All right, buckle up because today we're taking a deep dive into the periodic table of elements. You know, that iconic chart hanging in science classrooms worldwide. And sure, we've all encountered it before, but how many of us truly appreciate the genius baked into its seemingly simple design?
It's true. The periodic table is so much more than just a list of elements. It's a roadmap, a decoder ring to the very building blocks of our universe.
Exactly. And it all starts with a simple number, right? The atomic number.
Right. The atomic number, or the number of protons in an atom's nucleus, is the bedrock of the periodic table. It's the organizing principle, the foundation upon which everything else is built. And it's elegantly simple. Change the number of protons, and you fundamentally change the element itself.
Okay, that makes sense. But let's talk about how this actually translates to the table itself. We've got rows, we've got columns. It's like a giant spreadsheet. What's the method behind this organizational madness?
Well, the rows, known as periods, illustrate a fascinating trend. As you move across a period from left to right, you'll notice a general decrease in metallic character.
So we're essentially moving from those shiny, super reactive metals on the left side, like lithium and sodium, to the less metallic elements on the right, finally ending up with those aloof noble gases.
Precisely. It's like a spectrum of elemental personalities. But then we get to the columns or groups, and things get really interesting. Elements within the same group often exhibit remarkably similar chemical behavior.
Now, that can't be a coincidence, right? There's got to be some underlying reason why elements in the same group act like long-lost siblings.
There absolutely is. Remember those electron configurations we briefly touched upon?
Right, the way electrons are arranged within an atom. It's like each element has its own unique fingerprint based on its electrons.
Exactly. And what makes the periodic table so ingenious is that it visually represents those electron configurations. You see those columns, those groups, they often share similar chemical behaviors because they have the same number of valence electrons.
Okay, back up a second. Valence electrons, those are the ones on the outer shell of an atom, right? The ones that are actually interacting with other atoms, forming bonds, making all the chemistry happen.
That's it. Think of it like this. Each atom has these inner electrons that are content, staying close to the nucleus. They aren't really interested in interacting. Then you have the valence electrons, those social butterflies in the outermost shell, always ready to mingle, always looking to pair up and create bonds. They are the driving force behind chemical reactions.
So the periodic table isn't just about organizing elements. It's about understanding their social lives. But how do those electrons know where to go within the atom? Is there some kind of microscopic dating app for electrons? Looking for another electron to share an orbital with must love low energy levels.
Well, you can think of it more like filling seats in a theater, remember? Electrons want to be in the lowest energy state possible, so they'll fill those seats or energy levels, starting with the ones closest to the stage, our nucleus. And just like in a theater, some rows have better views than others.
Okay, so the rows are like energy levels. But how do those sections or subshells play into this analogy?
Excellent question. Those subshells are like the different seating sections within a row: orchestra, mezzanine, balcony. They have slightly different energy levels within the same main energy level. And just like some people prefer aisle seats, electrons have preferences for specific types of subshells based on their energy.
So elements in the same group of the periodic table, they have the same number of those outer shell social butterflies, those valence electrons. And since those are the electrons that primarily interact with the world, it stands to reason that elements in the same group would act similarly. They've got the same social circles, so to speak.
Precisely. It all comes back to those valence electrons and their eagerness to interact. They are the life of the chemical party, and the periodic table gives us a sneak peek at their guest list.
This is blowing my mind. The periodic table isn't just a pretty arrangement. It's practically a cheat sheet for predicting how elements will behave.
You've hit the nail on the head. That predictive power is one of the most remarkable things about the periodic table. For example, take atomic radius.
Hold on. Atomic radius. We're talking about the size of an atom here, right?
Yeah.
How much space it occupies.
Exactly. Think of it as the average distance between the nucleus and the outermost electron shell. Now, here's where it gets interesting. As you move across a period from left to right, atomic radius generally decreases.
Wait, the atoms get smaller as you add more protons and electrons? I would have guessed bigger. Why is that?
It's all about the tug of war between that positively charged nucleus and the negatively charged electrons. As you move across a period, you're adding more protons to the nucleus, increasing its positive charge. This strengthens the pull on the electrons, drawing them in closer and resulting in a smaller atomic radius.
So it's like adding more players to one side of a tug-of-war rope. The nucleus side keeps pulling the electrons closer. Okay, that makes sense. But what about when we move down a group? Does the trend hold up?
Interestingly enough, it reverses. As you move down a group, atomic radius increases. Think of it like adding layers to an onion.
Okay, I'm visualizing an onion. Go on.
Each layer represents an additional electron shell. Even though the nucleus gains more protons as you descend, those outer electrons are now occupying higher energy levels farther away from the nucleus. So despite the stronger pull, the additional electron shells make the atom bigger overall.
So we've got atomic size trends. What other patterns can we glean from the table?
Well, there's ionization energy, which tells us how much energy is needed to remove an electron from an atom. Interestingly, it follows a pattern similar to atomic radius.
So the smaller the atom, the harder it is to pluck away an electron.
Exactly. Those electrons are held much tighter in smaller atoms due to the stronger pull from the nucleus. Therefore, they require more energy to remove. Larger atoms, on the other hand, have those outer electrons further away, making them easier to snag.
Like plucking a grape from a loose bunch versus prying one off a tightly packed stem. So bigger atom, less energy needed to snag an electron. What other fascinating trends does the periodic table hold?
Let's talk about electronegativity.
Now, that's a word that sounds both intriguing and slightly intimidating. Break it down for us. What's electronegativity all about?
Imagine it as an atom's appetite for electrons when it's part of a chemical bond. Some atoms, like those in chemical bonds, like to share electrons. Electronegativity measures how strongly an atom attracts those shared electrons towards itself.
So some elements are like, those electrons look tasty. I'll have a bit more of that. Thank you very much.
Oh, precisely. And the king of this electron hoarding is fluorine, sitting up there at the top right corner of the periodic table. It's the most electronegative element with a voracious appetite for electrons.
So fluorine is like that friend who always steals the last bite of dessert. We all know one. But how does this electronegativity play out in the real world? Why should we care about an element's electron appetite?
Well, this is where it gets really fascinating. Electronegativity differences between elements dictate the type of bond they form, influencing everything from melting points and solubility to the very reactions they'll undergo. For example, elements with large differences in electronegativity tend to form ionic bonds, like sodium and chlorine in table salt.
So understanding electronegativity is like having insider information on how elements interact and form the compounds we see around us. It's like the periodic table unlocks this whole hidden language of chemistry.
Precisely. And just when you think you've got it all figured out, the periodic table throws you a curveball. It's not all neat trends and perfect predictions. There are exceptions, quirks in the system that keep things interesting.
Okay, I'm all ears. Tell me about the rule breakers of the periodic table. What makes them so fascinating?
Okay, so these exceptions, these rule breakers, they're what really make things interesting, right? Like, if everything perfectly followed the rules, wouldn't chemistry be, well, kind of boring?
Absolutely. The exceptions often reveal even deeper insights than the rules themselves. They force us to refine our understanding, to look for those underlying principles that might explain these seeming contradictions.
Right, like we talked about earlier with helium, right? Hanging out with those noble gases despite having only 2 valence electrons. Exactly. It's a perfect example of how a full outer shell trumps those simple electron count rules.
It's like helium found a loophole in the electron configuration rulebook and said, yeah, I'm going with the cool kids, those noble gases. But what other fascinating anomalies are lurking within the periodic table?
Well, there's that ongoing debate about the lanthanides and actinides, those 2 rows often relegated to the bottom of the table.
Oh, you mean those 2 rows that always seem like an afterthought, like footnotes on the periodic table? What's the big debate about their placement?
It all comes down to where their electron configurations fit most logically. You see, the lanthanides and actinides, also known as the F-block elements, are like the introverts of the periodic table, preferring to keep their quirky electron configurations hidden away in those orbitals.
Okay, so they're a bit shy, like to keep their electrons close to the vest. But why is that such a big deal for their placement on the table?
Well, some argue that shoehorning them into those 2 rows below the main table doesn't accurately reflect their electron configurations or their chemical similarities.
So it's not just about aesthetics, it's about accurately representing their chemical DNA within the structure of the periodic table, right?
Exactly. And there are a number of proposals for rearranging the table to better accommodate the F-block elements. Some suggest simply shifting them one element to the right, while others propose more radical redesigns.
Wow, so it's like trying to find the perfect spot for a couple of oddly shaped pieces in a jigsaw puzzle.
Yeah.
It really highlights how the periodic table is a work in progress, constantly being refined as our understanding of chemistry evolves.
Precisely. And this exploration takes us beyond the known elements. What happens when we reach the edges of the periodic table as we know it? What lies beyond the seventh row?
Okay, now we're getting into truly uncharted territory. What happens when scientists start synthesizing elements that are so heavy, so exotic, they make uranium look like a lightweight?
That's where things get truly mind-blowing. We're talking about super heavy elements, those at the very fringes of the periodic table, pushing the limits of our understanding of physics and chemistry.
So the periodic table isn't finished. There's still room for expansion, for new elements to be discovered, or in this case, created.
Absolutely. But synthesizing these super heavy elements is incredibly challenging, like trying to hit a bullseye on the moon with a grain of sand.
Wow, that's quite the analogy.
It requires incredible ingenuity and incredibly powerful particle accelerators, smashing atoms together at near light speeds with the hope that they'll fuse and create these new elements.
And even if they do manage to create these new elements, they're often incredibly unstable, right? Like,
Yeah.
here 1 minute, gone the next.
Exactly. These super heavy elements exist on the very edge of existence, often decaying in fractions of a second.
So it's a race against time to study these exotic elements, to unravel their secrets before they vanish into thin air. What are some of the big questions driving this quest for super heavy elements?
One of the most intriguing questions is whether the patterns and trends we observe in the current periodic table hold true for these super heavy elements. Will the eighth row neatly follow the established order, or will those relativistic effects we talked about earlier throw everything into disarray?
Wait, so Einstein might actually mess with the periodic table? That's wild.
You better believe it. As we get to these super heavy elements with electrons whipping around the nucleus at significant fractions of the speed of light, Einstein's theories of relativity come into play. And these relativistic effects can dramatically alter an element's properties, potentially turning everything we thought we knew about periodic trends on its head.
So we might need a whole new periodic table, a whole new understanding of chemistry to accommodate these super heavy elements. It's amazing to think about these tiny elements challenging the very foundations of our scientific understanding.
It's a humbling reminder that science is a journey, not a destination.
This deep dive has been an incredible journey. We've gone from those familiar squares on the classroom wall to the very frontiers of chemistry, where Einstein and unstable isotopes collide. It's truly mind-blowing stuff.
It is. It's a testament to human curiosity, our relentless drive to understand the universe and our place within it.
So what does this all mean? What's the takeaway from our deep dive into the periodic table? What should our listeners ponder as they go about their day?
The periodic table is far more than just a chart. It's a testament to our quest for order, our desire to find patterns and meaning in the world around us. But it's also a reminder that the universe is full of surprises, exceptions that challenge our assumptions and drive us to keep exploring.
It's a story that's still being written, one proton, one neutron, one electron at a time, and who knows what incredible discoveries await us as we continue to explore the boundless frontiers of chemistry. Thanks for joining us on this deep dive into the heart of the elements. We'll see you next time.